This is the first video I'm making for you guys to clarify things that are not clearly explained in the book or skipped over or made unclear in the other videos that I show you. So the first thing I'm going to do here is show you the conventions that they use for vectors, because it turns out that when we're talking magnetic fields, especially when they deal with electric currents, that we're dealing with 3 dimensions. So it doesn't all fit neatly onto a flat page. And sometimes we have vectors that go into the page, and sometimes they come out of the page. So here's the convention here. If a vector is going into the page, it is represented by an X, which means whatever is happening is going down into the page away from you. So this is into the page. And then if the vector is coming out of the page, emerging out of the page toward you, it is just a dot. So this is out of the page, out of page. Now, how can you remember which is which? Well, where this comes from is from an arrow, an archery arrow, like you've used in gym class. So the idea is you have an arrow here with an arrowhead on it. And on the back, there's the fletches, the feathers. And if you look at this thing from the back side, what you're going to see is the core of the arrow with the 4 feathers as the arrow is moving away from you. So this, the vector moving away from you into the page, looks like the feathers on the back of the arrow. Now conversely, if you're looking at it from the front, all you're going to see coming toward you is just a little point. That's kind of a horrifying thought, but go with me on it. Anyway, so if the arrow is actually coming toward you, it's just a little dot, and that's coming toward you. That's how where the convention comes from, and that's how we can remember it. So this is a dot. So we'll start here. This is on magnetic fields, and the explanation in the book is obviously very good, but it skips some background information which I think helps it all make a lot more sense. So we're going to talk about magnetic fields here for a couple minutes. Now we're going to start off with something that we're already familiar with, which is electrical fields, because we've looked at electrical fields before. And as you remember, an electrical field exists between a positive and a negative charge in some way. And we have a field which runs from the positive charge to the negative charge, and it makes a fairly familiar pattern here that you'll recognize. As you recall, it kind of goes out all in space so that it encompasses as far as you want to go. Now the direction of an electric field is from the positive to the negative, which is why we can put arrows on these field lines to show the direction that they pass. And it has a distinctive shape like this. Now we're going to move to magnetic fields, and a magnetic field is generally, we're going to start off with a simple version here of around a simple bar magnet. We're going to put the North Pole up here and the South Pole down here. And as you've probably seen from playing with magnets and iron filings in earlier classes, field lines run in patterns which look very similar to electrical field lines. They make these kind of ovals that pass around, and they get weaker the farther you go away from the magnet, but they do take distinctive shapes like this. Now, magnetic fields do have a direction, and the convention on this is that the direction runs from the North Pole to the South Pole. Okay? So the magnetic field lines emerge from the magnet at the North Pole. They come around, follow these patterns, follow these lines, and re-enter the magnet at the South Pole. And it looks similar to the electric field, and that's why we start. But there are some very important differences between magnetic fields and the electrical fields. First, electrical fields start at the positive and end at the negative. So the field lines for an electrical field have a start and an end. And magnetic field lines are not like that, because even though we can see them emerge from the north and come back to the south, if we look inside the magnet, we'll see these field lines proceeding from the south to the North Pole inside the magnet, like this. And what this means, I should loop that around so it looks like a complete loop. What that means is that magnetic field lines are complete, continuous, unbroken loops. And part of the magnetic field we see outside the magnet, and the rest of the field line exists inside the magnet. So we have complete, unbroken lines of magnetic force. Now when we have a solid magnet like this, it seems kind of what are we talking about as far as complete loops if you can't get to some of them? But we're going to see as we move forward, especially when you have magnetic fields around coils of wire, or around straight wires, which we'll see soon, we do have complete unbroken magnetic field loops that exist in space. They don't pass through anything. So to summarize, magnetic field loops are unbroken loops, unbroken, complete loops. The direction of the magnetic field is from north to south, outside a magnet, and south to north inside a magnet. Now this becomes necessary because sometimes we care about the direction of a magnetic field, and if we want to make connections between a magnetic field we see around a wire or inside a solenoid or something like that, and make connections between that and what it would look like with a solid magnet, it's a good idea to remember these things. So the direction of the magnetic field is north to south when you're outside the magnet, and south to north when you're inside the magnet. Okay, now the Bozeman video that I assigned to you jumps around a bit between the magnetic field around a straight wire and the magnetic field in a loop. It kind of goes back and forth a little bit and it gets a little confusing. Now the problem that he has is he doesn't make it clear how you go from the field around a straight wire to the field around a inside a loop. So on page 772, that's 772 in your book, they have this diagram here, and it does a pretty good job of explaining how the field works inside a single loop. Now, we have the right-hand rule for field, which is where you lay your thumb in the direction of the current, and in this case the current is coming out of the page at us here because it's just a dot at that point, and then the fingers curl in the direction of the magnetic field. So if we look at this point right here as a single wire coming out of the page toward us, we can see using the right-hand rule that the magnetic field makes complete loops in this direction. Counterclockwise as we're looking at the page. Now down here at the bottom, the loop of wire has come out of the page and is now re-entering the page at this point. So now the current is going away from us. So you kind of have to visualize this. Now the current is going into the page, and that means that the magnetic field is going clockwise as we look at it here. So what that means is when we have a loop, we have a magnetic field which runs through it from one side through the hole in the middle out the other side. And the direction that that magnetic field goes through depends on the direction of the current in the loop itself. And that is a single loop. This is the same thing shown from the side. The current in this case is going counterclockwise, and the magnetic field is coming out toward us through the middle of the loop and is going away from us into the page on the outside of the loop. So it's sort of like a donut that we're looking down into, with the magnetic field lines coming toward us in the middle and away from us on the outside. Now that makes perfect sense, I guess, for a single loop. But what happens when you start stacking a bunch of these loops on top of each other like a roll of lifesavers? Okay, so now we've moved to page 773. That's the opposite page, and it shows what's called a solenoid, which is a stack of loops, like I was saying, sort of like a roll of lifesavers with a whole bunch of loops stacked on top of each other. Now, the way they actually construct these things is by a coil of wire, so it's this long, continuous spiral of wire that goes around and around and around. And in this case, let's see, the current is coming out toward us at the top of this and going into the page at the bottom. You'll be able to see it in your book, but there's dots up here at the top and X's down at the bottom. So the current is coming around like this as we look at it. Now the thing that you have to understand is that each individual loop will make a magnetic field like we saw on the opposite page on 772. But when you stack these loops together like lifesavers, as I was saying, the magnetic fields kind of stack up and reinforce themselves. So rather than having a field that goes around each individual little wire, they all kind of join up and they make a single magnetic field which sweeps down the middle of the through the middle of the tube. So it goes through the tube in one direction to our right here in this diagram through the middle of the coil, and then it loops around the outside on the outside of the coil. again, with just like electrical field lines, the closer together the lines are, the stronger the magnetic field. So you have a pretty intense magnetic field inside the solenoid. Now, one other thing to point out here is that this looks just like the diagram of a bar magnet. The magnetic field lines are coming out of this end, looping around the outside, and coming in here, and then they travel up the inside of the loop. So this would be like the North Pole over here, if it was a bar magnet, and this would be just like the South Pole of the magnet over here. But the solenoid behaves pretty much the same way that a bar magnet does, in principle at least. Now, the nice thing about this, the solenoid, is that it's a magnet that only exists when there's an electric current flowing, which means you can turn it off. That's not something you can do with a regular bar magnet, but if you use electricity to make your magnet, you have a magnet you can turn on and turn off. Now, the magnetic field produced by a solenoid, that is just a coil of wire with electricity running through the wire, the magnetic field produced by that is actually quite weak. And it turns out we can make the magnetic field much stronger if we put an iron core, a steel or an iron core, inside that coil. And you've probably played with this before. It's called an electromagnet. And if you wrap the solenoid around an iron core, it makes the iron bar, the iron core, very strongly magnetic. Now, it turns out that the magnetism has always been inside that iron all along. It's just that it's been in individual domains, which you probably remember from an earlier video. And the magnetic fields of each of those domains is not aligned. But when you put the iron core inside a solenoid, the magnetic field from the solenoid kind of twists all the domains around and gets them lined up with each other and makes them work together. So the existing magnetism that's already inside the nail is now all working on the same page. They're marching together, if you will, and it makes a very powerful magnet. It makes a much more powerful magnet, I should say. But again, it has the advantage of when you turn off the solenoid, it makes the magnetism in the nail, for the most part, disappear. Now, if you put a strong enough magnetic field around the nail, a strong enough solenoid, a powerful enough solenoid, then the nail itself will become permanently magnetized. And this is how they make permanent magnets. You just have a really, really strong solenoid with a lot of current running through it, and the nail or whatever iron core you use will remember, and it will become a permanent magnet, because those domains will remain aligned even when you take away the electric current and the solenoid's magnetic field.